Welcome back. In this lecture, we're going to talk about acidity and basicity with a special emphasis on comparing and predicting relative acidity and basicity of the three kinds of acids and bases we discussed in previous lectures. The required reading is chapter 6. All right, so shown here is a generic equation showing acid dissociation equation in water. So Ha react with water to produce H3O plus and A minus. Okay. Now, if you write down the equation for the equilibrium constant, you will get the following equation: Ka equals H3O plus multiply A minus divided by Ha concentration. Okay, and one thing you notice is that the concentration of water is neglected here because it is a constant in dilute solutions. So typically, the concentration of water is not shown in the expression of equilibrium constant. This equilibrium constant can be pretty large, can have a pretty large ranges. An alternative way to express it is to use the so-called pKa. So that is negative log 10 of the Ka value. So a large Ka for the acid, a large Ka corresponds to a smaller pKa because there's a negative sign here in the expression. And the large Ka indicates that acid likes to dissociate in water. Okay, so that corresponds to a stronger acid. Now, the stronger acid would have smaller pKa. Okay, so make sure you use the correct term when you do the comparison. Now, when we write down the equation here, we're actually using water as a reference. So Ha is the acid and water is the base. So you always need a reference point when you write down equations like this, because the acid in a solvent system cannot dissociate on its own. It has to react with another base. Okay, so in a solvent, this base is typically the solvent itself, but you are not limited to the solvent. You can use other reference acid or bases as you wish. Okay, so in the following discussion, you will see examples where people use, for example, boron trifluoride, a Lewis acid, as the reference to quantify the basicity of different kind of bases. All right, you can write down a similar equation for the gas phase reaction. So in the aqueous system, in the solvent-based system, there's this protonation of water, but in the gas phase, you don't have to do that. If you have a gas phase acid, you can, in theory, measure the autoionization of the acid into its conjugate base and a proton, both in gas phase. Now, there's a big difference between the two. Between the two processes, in that in a solvent there's a lot of solvation effect going on. The charge separation during the ionization process is very energy intensive. Now in a solvent, that energy penalty is compensated partially by the solvation of the solvent molecules. Now in gas phase, there's no such solvation. So the overall trend in acidity and basicity in the solvent and in the gas phase could be very different. Okay, we're gonna look at a couple of examples in the following slides. Now in the gas phase reaction, we can write down the equation like this, and there will be corresponding change of Gibbs free energy and enthalpy, and the Gibbs free energy would be will be used in our definition of acidity. Okay, so again, in this case, a smaller delta G corresponds to higher acidity. Okay. All right, now let's look at a couple of examples of gas phase basicity. Okay, so this table is taken from the text. It lists a bunch of base molecules and the corresponding GB value. GB is similar to the GA value we discussed in the previous slide. It's basically the Gibbs free energy change for the ionization of protonated base into the neutral base and a proton. Okay. So in this case, a high GB value, okay, a high GB value in this case indicates the base is stronger, okay, because it means the protonated base is less likely to dissociate. Okay. All right, so if we look at this list of numbers, what I have highlighted are four: ammonia, methylamine, dimethylamine, and trimethylamine. And what you find is in this series of four molecules, you basically start with ammonia and replace each hydrogen atom with methyl groups, okay, one by one. So trimethylamine has three methyl groups, dimethylamine has two, methylamine has one, ammonia has zero. And if you look at their GB value, you'll find that there's a perfect trend in that the more methyl group you add, the higher the basicity you will get. And this can be understood pretty straightforwardly by considering the inductive effect. Okay? The inductive effect basically says if you have ligands on the central atom that are electron pushing, then you would expect the electron pushing group would increase the electron density on the central atom, and that would make the central atom, in this case nitrogen, more likely to accept a proton. And what that means is the basicity would increase. If you have electron withdrawing group, on the other hand, you would expect a decrease in the electron density on the central atom, and that would in turn produce less a tendency for the central atom to accept a proton. So that would lead to a decrease of basicity. So if you look at the table again, you'll find a lot of these trends out there. So for example, there's also ethylamine, diethylamine, and triethylamine. And you'll find they follow exactly the same kind of order. The more ethyl group you have, the more basic the molecule becomes. So to understand the inductive effect, you should probably go back to your organic chemistry lecture notes and think about and refresh yourself about which functional group is electron donating and which function group is electron withdrawing. So alkyl groups, for example, are electron pushing relative to hydrogen. Halogen atoms, again, relative to hydrogen atom, is electron withdrawing. Okay. And you'll find some of the electron withdrawing groups here as well. So if you look at, for example, pyridine, okay, there's 2 bromopyridine and 2 chloropyridine. And both are less basic than pyridine itself. That's because bromine and chlorine are both weakly electron withdrawing groups when attached to the aromatic ring. Things in the aqueous system are a little bit more complicated. The reason, again, is because the solvation effect we mentioned just now. Okay, so if you look at this table lists the pKbH plus value. Okay, so this is essentially the pKa value of the conjugated acid of the base molecules listed here. So in this case, a high pK value corresponds to a stronger base because it means the conjugated acid is less likely to dissociate in water. Okay. So if you look at this table, you'll find the same kind of substituted ammonia. This list of substituted ammonia showed a different sequence. Now, in this case, in water, dimethylamine is the strongest, and followed by methylamine, and followed by trimethylamine, and followed by ammonia, which is not listed in this table. Now, if you compare this sequence with the basicity sequence in gas phase on the right hand side of the slide, you'll find the biggest change is trimethylamine. Okay. Trimethylamine is the strongest base in the gas phase, but becomes much weaker in aqueous solution. Why? Because trimethylamine is a lot bigger than the other three molecules, and it has three methyl groups. Now we know methyl groups are more like oil, it's hydrophobic, so it doesn't like to interact with water. And what this means is trimethylamine will experience much less solvation when it accepts a proton to become trimethylamine ammonium ion. Now, if the product is less stable, it will be less likely to accept a proton to produce the cation, and that makes the trimethylamine a much weaker base than one would expect, based solely on the induction effect. Okay, so this is a very classical case of solvation changes the sequence of basicity. There are many other examples of inductive effect impacting the acidity and basicity of molecules. Shown here are two other sequences you can find on the text. On the top are pK values listed for 4 acids, and the common feature of all those acids are the central atom, which is chlorine, and the difference between them is how many double bond oxygen are attached to the chlorine atom. Okay. So for HClO4, this molecule has 3 double bonded oxygen and 1 hydroxyl. And for HClO3, there are 2 double bonded oxygen, HClO2, 1 double bonded oxygen, and HOCl, there's no double bonded oxygen. Okay. Now, oxygen is highly electron negative, and when you have a lot of those oxygen atoms attached to the chlorine atom, you would expect the oxygen would strongly pull the electron away from the hydroxyl, okay, and that will make the molecule easier to release the proton. On the bottom shows 5 species and their corresponding pK value. In this sequence, there are 2 trends I want to discuss. One is between the same acid, so H3PO4, H2PO4-, and HPO42-. The trend here is pretty easy to identify, in that the more negative charge there is, the higher pK value it is, which means a high negative charge would correspond to a weaker acid. And this is pretty easy to understand because proton is positive charge. So if the parent molecule has a lot of negative charge, it would make it difficult to release a proton from itself. There's another trend that I want to point out, in that H3PO4 and H2SO4, their central atoms are next to each other in the periodic table. Okay, phosphorus is to the left of sulfur. Now, if you look at their pKa value, you'll find sulfuric acid is a stronger acid than phosphonic acid. Why? Because sulfur is a much more electronegative atom than phosphorus. So having an electronegative atom as a central atom would likely to stabilize the negative charge produced after the ionization, and that would lead to the prediction that the more to the right hand side of the periodic table, the more likely you will see a stronger acid. All right, on this slide, I showed two molecules, pyridine and aniline. And if you look at these two molecules, you'll find their sizes are similar and the structures are similar too, with one important exception. In pyridine, the lone pair of nitrogen does not have any interaction with the pi system. In contrast, in aniline, the lone pair of NH2, the nitrogen, can form partial conjugation with the pi electron of the benzene ring. Now, this interaction would make the lone pair of aniline much less likely to accept a proton compared to the case of pyridine. And the prediction would be pyridine is a stronger base than aniline, which is what the experiment observes. Steric effect can be important in cases where large acid-base molecules react with each other. In aqueous system, this is typically not an important factor because proton transfer is what happens in aqueous acid-base reactions, and proton is really small. So in those cases, inductive and solvation is much likely to dominate the relative acidity and the basicity. However, in the case of Lewis acid-base interaction, you're much more likely to find much larger molecules interacting with each other, and in those cases, steric effect can be very important. On the table on the left, I listed proton affinity and affinity to boron trifluoride for 4 amines. The proton affinity is the gas phase proton affinity we discussed before. Here, the more methyl group you have, the higher proton affinity you would expect. If you look at the affinity to BF3, you'll find the order is very different. For example, trimethylamine has the highest proton affinity, but its affinity to BF3 is only the third. And the reason being, trimethylamine is the largest base, and the 3 methyl groups around nitrogen makes it difficult to interact with the boron atom on BF3, and that makes the interaction between nitrogen and boron much weaker than, for example, in the case of dimethylamine. In the last section, I want to introduce a new concept called hard-soft acid-base theory, HSAB in short. This is a qualitative and quantitative approach to predict and understand the interactions between Lewis acids and bases. Now, in our lecture, we're going to limit our discussion to the qualitative aspect of the theory. The idea here is pretty simple. We categorize Lewis acids and bases into 2 kinds, hard and soft. A hard Lewis acid or base are those molecules or ions that are less polarizable. They're typically small, and they are more ionic in nature, okay, in terms of their interaction with other species. Soft acids or bases are the opposite. They're much more polarizable. They're typically much larger. And in terms of their interaction with other species, there's more covalent interaction in nature. Now, the essence of the HSAB theory can be summarized into one sentence. That is, a hard acid prefers to interact with hard base, and vice versa, and a soft acid prefers to interact with soft base, and vice versa. So this gives you a very simple and straightforward way to predict relative interaction magnitude of different Lewis acid pairs if you know whether those Lewis acids or bases are hard or soft. This slide shows the common Lewis acids and bases and grouped them into hard, soft, and borderline. On the hard acid side, you will find proton and everything in the alkaline metal and alkaline earth category, as well as highly charged first row transition metal ion. On the soft acid side, you'll find those heavy transition metal ions. A lot of them have a low charge, either 1 plus or 2 plus, with the exception of platinum 4 plus. These ions, they are much larger, either because of their low positive charge or because of their location in the periodic table, are much larger than the highly charged early transition ions in the hard acid category. And in between are borderline acids, and some of those examples are lowly charged first row transition metal ions, such as iron 2 plus and cobalt 2 plus. In the base category, for the hard base, you'll find fluoride, chloride, and a lot of ions having oxygen as its major components. Okay, so a lot of the strong acids, their corresponding anion are hard bases. Okay, examples are nitrate, perchlorate, carbonate, sulfate, phosphonate. A lot of nitrogen-terminated bases are also considered hard. Examples are ammonia. On the right-hand side are soft bases. The most prominent ones are those related with sulfur and iodide. Carbonyl, carbon monoxide, is a very important soft base, especially in transition metal complex chemistry. Also, phosphorus is an important soft base atom. Phosphine, so PR3, and related arsine, ASR3, are very important ligands in transition metal complexes. Last but not least are acetylene and benzene. Those two molecules, even though we did not discuss this in previous lectures, can use their pi electron to interact with Lewis acid. And all pi systems are usually soft bases. All right, so again, somewhere in between, there's borderline bases. The most interesting example here is bromide, and you see the transition here. Fluoride and chloride are hard bases. Iodide is soft base, and bromide is the borderline. Another transition you can find is comparison between ammonia, which is hard base, and pyridine, C5H5N, which is borderline. And you can see how the electronic structure and the molecular structure impact the hardness of the base. HSB theory can be very powerful and useful because, as we explained in the lecture, every chemical reaction is a Lewis acid-base reaction. So in principle, you can use HSB theory to explain all chemical reactions. And shown here is probably the most famous example. It shows the KSP, or solubility product, of 4 silver compounds: silver fluoride, chloride, bromide, and iodide. And the overall trend here is very clear. Silver fluoride is highly soluble, so high KSP indicates a soluble compound, and low KSP indicates an insoluble compound. As you go down the periodic table, silver chloride, bromide, iodide becomes less and less soluble. Okay, and why is the case? That's because silver is a soft acid, so it likes to stay with soft base. Now, which base is the softest? That is iodide. So what that means is silver iodide should be the most stable one. And fluoride, being a hard base, forms the least stable compound with silver fluoride, and that means the solubility of silver fluoride should be the highest. All right, so that will conclude our discussion today. A brief overview of my expectation. In this lecture, we talked about all kinds of factors, inductive, solvation, steric, that could impact the acidity and basicity of molecules. I would expect you to understand those factors and be able to identify relevant factors when a series of molecules is presented to you. I expect you to be able to explain the trend in acidity or basicity, or the lack of a trend in a series of molecules by using those factors. I expect you to know the common hard soft acid bases. You do not have to know every Lewis acid base in those two tables, but you should have a general idea what is the characteristic of hard acid and hard base, which part of the periodic table you are most likely to find the hard acid or hard base. And if given two Lewis acid and bases, you should be able to have a general idea which one is harder and which one is softer. And last, you should be able to use HSB theory to predict reactivity trends, thermodynamic data. As I said, every chemical reaction can be explained by Lewis acid-base interaction. So you should be able to use HSB theory to explain pretty much everything. All right, that will conclude our discussion today. I'll see you in class, and please let me know if you have any questions through email between now and then. Thank you.